Okay, thermodynamics. That is the chapter, right? That is the chapter being discussed in class. Okay, let's begin. Thermodynamics. There's three main quantities in this chapter that you'll be dealing with. The first one is what is it? Enthalpy. The second one's entropy. And the last one is free energy. Enthalpy denoted by H. Don't ask why. Oh, do ask why, because if you denoted it with E, E was already taken for energy. So come up with something else. Entropy, S, once again, can't use E. Free energy, can't use F, can't use E, and so G. This has historical context. It's Gibbs free energy, so the G comes from the chemist who came up with the concept. Oftentimes, we'll only be all of the time we'll be interested in the difference in enthalpies, not in their absolute value, just the difference going from here to there. And since we're dealing with chemical reactions, the enthalpy going from the reactants to the products. That's all. If any of these changes are measured at standard conditions and temperatures, you just put a little that over just to say that it's at standard temperature and pressure. Whoops. And I think I mentioned early on that standard temperature and condition are not uniform. They're different depending on what chapter you find yourself in. In thermodynamics, standard is 1 atm and 0 degrees Celsius. Yeah. When you get to electrochemistry, that's when it's 25 degrees Celsius. Okay, anyway. Now, the first thing is, what are these three things qualitatively? What do they help you describe? And so let's answer that real quick. Why do we care about these quantities? We care about enthalpy because enthalpy tells you about the heat of the reaction, how much heat is absorbed or released as a reaction takes place. Entropy deals with the disorder of any kind of change. Does disorder go up or down? And then free energy deals with what's called, there's many reasons why this is useful, but our main reason will be spontaneity. Which is the question that if I mix two reactants, will a reaction take place immediately on its own without any other help? Or will I have to first heat it up or put a spark or something or burn it or whatever, right? Does it happen by itself? That's spontaneous. Okay. And in each case, the sign tells you different things, right? So delta H could be positive or negative, delta S could be positive or negative, and delta G could be positive or negative. If delta H is positive, heat is, you tell me, absorbed or released?
Absorbed.
Heat is absorbed, and what do we call such a reaction?
Endothermic.
Endothermic, exactly. All right. So this one must be where heat is released, and it is exothermic. Another thing that I want you to associate with delta H sign is that when heat is absorbed, you should think of the temperature going down, temperature of the surrounding going down, And when heat is released, the temperature of the surrounding goes up. Okay. With delta S, the signs follow what we expect. If it's positive, entropy increases. If it's negative, entropy decreases. There's nothing there. And then lastly, with delta G, a positive delta G tells you that the reaction is not spontaneous. It needs extra help to get going. And negative if it is spontaneous. Okay. Great. So let's do some qualitative metrics. Mm-hmm.
At the top of this, you had written something, and I couldn't quite read it.
Where? Here?
Above the G.
Above the G. Gibbs. That's where the letter G comes from. Gibbs free energy, yeah.
And the other thing you wrote at the top, at 1 atm and 0 degrees Celsius?
That's standard conditions. And those are standard conditions in thermodynamics. Yeah, the key thing to remember is that when the next chapter it will be 25, not 0. Yep. All right. All right, some qualitative remarks. So qualitatively figuring out sign. Qualitative okay, let's just say determining sign qualitatively. For delta H, it's pretty simple, right? You just see if heat was released or absorbed. You can feel it. You can use your thermometer to figure out what happens. Same thing with delta G. Delta G is pretty easy to figure out. For example, as a kid, you might have mixed vinegar and baking soda. It immediately starts to bubble. That's a spontaneous reaction. You don't need to do anything. So delta G is pretty easy to figure out the sign of. The tricky one is delta S, and that's what we'll talk about. So let's talk about processes that increase entropy. Here's some of them. Mixing. Any kind of mixing will always increase entropy. That's pretty simple to understand. Initially, you had the pure components, and now they're mixed. There's more disorder, there's more chaos now. Does that make sense? Yep. So any kind of mixing will increase entropy. If you go from gas to liquid to solid, no, the other way. Solid to liquid to gas, entropy goes up. Oops. Which is to say solid has the least entropy because it's so ordered and, the molecules are not really flying around everywhere. They're stuck together. Liquids have a little more freedom, so liquids have higher entropy. And then gases just go crazy. They have the highest entropy. So as you transition from solid to liquid to gas, the entropy increases. Another one is for gases, no, for anything, a temperature increase corresponds with entropy increase. Think about it this way. If you have a balloon of gas, two identical balloons of gas, one is in the refrigerator when one is outside in the hot sun. The one in the refrigerator, the molecules have low energy because it's cold, and so they're moving around, they're flying around, but lazily. They're not moving around as fast as they can. But the ones outside in the hot sun are really flying around fast. If you fly around fast, you're creating more commotion, more entropy. Right? That's the idea. So it takes a little bit of getting used to the notion of disorder and what disorder constitutes. A precise definition of entropy you will see if you take like a higher physics or chemistry course. There's a precise definition for entropy. TLDR, it is how many possible configurations a system can have. The more configurations a system can have, the more entropy. All right. And for gases, decrease in volume causes increase in entropy. No, the other way. Increase in volume causes increase in entropy. The reason being, well, molecules have more volume to access and fly around in. Right? So now a lot more configurations are possible, so the entropy goes up. So there's that. These are the 4 qualitative metrics you'll use to figure out if entropy increases or decreases. If entropy increases with these processes, entropy decreases in the reverse processes. So as opposed to mixing, if you filter something, entropy goes down. If you go from gas to liquid or liquid to solid, entropy goes down. If you decrease temperature, entropy goes down. If you decrease volume while keeping temperature constant, entropy goes down. Okay, so there's that. Okay, so that's qualitative, easy to figure out. Let's move on to the meat of the chapter, which is reaction values from formation values. Reaction values from formation values. So if you have a reaction, let's say let me make it a little bigger. C6H12O6 plus 6O2 gives 6CO2 and 6H2O. Yeah, this is a good one. And oftentimes we'll be concerned with what is the delta H for the whole reaction. If the reaction takes place, how much heat is released or absorbed? And what you'll be given are the enthalpy of formation values for each of the species involved in the chemical reaction. Okay, so let's take a little pause here. What do formation values represent? They represent the enthalpy, entropy, and free energy required to form compounds to begin with. Right? So formation values is the enthalpy change associated with, the entropy change associated with, and the free energy change associated with forming a compound. Each compound has a formation value for all three of those quantities. Reaction values are when the compounds come together to react in a chemical reaction. Okay? And there's a very neat formula to go from formation values, which look like, so for enthalpy, formation values looks like delta H with a subscript F, F for formation, same thing with S for formation, and then G for formation. And the reaction values are with reaction as the subscript. So just try and connect these two big things in your head. And the equation goes as follows. The reaction enthalpy change is products minus reactants. So formation values of the products minus formation enthalpy values of the reactants with multiplied by coefficients. I'll tell you what that is in a sec. The coefficients from the chemical reaction. So each formation value is multiplied by the corresponding coefficient. You might have seen a more complicated looking formula in your thing, which goes like that. Products minus reactants with coefficient. I think it looks scary and complicated. It doesn't need to be. Okay. And the nice thing is the same exact formula holds for entropy and free energy. So I'm just going to copy this down, something that I can do. But you can't. Okay. And just replace the H's with S. So delta S reaction is delta S formation of the products minus SF for the reactants, and same thing with delta G. All right, here's a question. I'm just gonna write that same equation up there. If the delta SF for the following reaction are as follows. Determine delta S reaction. And same reaction, C6H12O6 plus 6O2 gives 6CO2 plus 6H2O. And here are the values. I'm just making up something. Here we go. Okay. If you notice, you'll see that I haven't given you a value for one of the species, and that's because that's something you can figure out on your own. And so let me go back up here and write down that the formation values, as a remark, for elements is always 0. The idea is very simple. Compounds are made from elements, so they have a formation process. What are elements made from? Yep, atoms, and yes, but chemistry doesn't go all the way down there. Chemistry starts with, I have elements to begin with, what can I do with them? Yeah, so that's why we just say that there's 0 to begin with in chemistry. Formation values for elements are always 0. And so delta HF of an element, delta SF of an element, and delta GF of an element are all 0s. With one caveat, are always 0 at standard conditions. If you change the temperature, story's a little different. At standard, so let me just put the standard symbol on all these. And let's say that these are the standard entropy values down here. Cool. All right, so let's begin. Delta S reaction. Does anyone want to take a crack at this? All right, so we'll do products minus reactants, right? So products get positives, reactant get negatives, and everything's multiplied by its own coefficients. Grace, let's go. So instead of values, let me just say this. Delta SF of, what should I look at first?
I don't know.
Products, right? What's your first product?
CO2.
CO2. And is there a coefficient for CO2? 6. Yep, 6. Okay, next.
6 H2O.
Yep, H2O, and there is a coefficient of 6. And then as soon as you start hitting reactants, you need to start subtracting. All right, delta SF of, tell me.
C6 H12O6.
Exactly. Any coefficients?
Plus 6O2. Oh, there's no coefficient.
Yeah. If you do plus, then you have to put overall parentheses for the products. If you want to be lazy, just continue positive for the products, negative for the reactants, just like equilibrium, if you think about it. Okay, and then tell me the last one.
6O2.
Yes. So of oxygen with a coefficient of 6. It's that simple. All right. Just plug in the values. We're done. 6 times negative 125. 6 times 50. Minus negative 100. Minus 6 times. Minus 6 times what? All the way at the end. Exactly. it's an element. Oh, I forgot my phone. It's outside. Yeah. Whatever this comes out to. Same story with enthalpy, same story with free energy. Okay. So there's that concludes that section. Oh, and then the next thing is that, did she cover this? Because if not, that will save us some time. Did she talk about when you add equations, the enthalpies add up? So on and so forth. By the way, is this all of thermodynamics that she's going to cover? Do you know that?
With the enthalpies adding up, I think we did that in Chem 1.
Right.
Yeah, so she didn't go over it. Like that slideshow has about 55 slides, but I think...
I see.
Yeah.
Yeah. Okay, we'll skip that.
I mean,
Okay.
it might be helpful if anyone else thinks that, but...
Sure. It's easy to cover real quick. Okay, so this section I'm just going to title Adding Equations Adds Their Delta H's, Delta S's, and Delta G's. Pretty simple concept. Here goes. Say carbon plus oxygen gives carbon dioxide. And let's say H2O plus CO2 gives H2CO3. This thing has a delta G reaction of, I don't know, negative 100. This thing has a delta G reaction of 200. If you add up the reactions, the delta G's add up. So reactants remain on the reactant side. Carbon plus oxygen plus water plus CO2 becomes CO2 plus H2CO3. And you can clean this up real quick. So carbon plus oxygen plus H2O gives you H2CO3 with a combined delta G reaction of negative 100 plus 200, which is positive 100. There's also two other things you can do. You can multiply an equation throughout by a number. So multiplying equations multiplies, same thing here. And then the last statement is that if you flip an equation, then each of these values flip. Let me just bring this down. Here's an example of that. If I take this first thing and now I want to write down the free energy of this reaction, which if you notice is exactly flipped, what would that be? I took this reaction and I flipped it. So what happens to its delta G?
Changes sign.
It flips, yes. Flips in the sense of changing sign. Yep, so it becomes positive 100. What if I take this bottom one and I make it 5H2O plus 5CO2 gives 5H2CO3. Alexandra? I can't hear you for some reason. Okay, I can hear you now.
Okay. You multiply it by 5.
Exactly. So what do I get?
200 times 5
Yep.
is some number. Yes, 1,000, of course.
1,000. Yeah. And then you can mix and match. You can flip and multiply at the same time and do stuff like that. Just keep track of the changes that you're making, and it's that simple. Yeah, so there's that. Any questions? Do you want to see another question with mixing and matching involved? No? Okay, pretty simple. Now comes the relationship. So far we have only been able to relate the reaction values to the formation values for enthalpy, entropy, and free energy alone. Now we're going to connect all three of those, delta H, delta G, and delta S, and come up with some very interesting observations. Relationship between delta H, delta G, and delta S. They're connected by this formula. Delta G equals delta H minus T times delta S. Okay. Where T is temperature. What kind of questions to expect? Well, you have 4 variables, delta G, delta H, T, and delta S. Expect questions where 3 are given and you're asked to calculate one of them. Pretty simple. Here's an example. If delta H reaction, let's say at standard conditions, is negative 100 and delta S reaction is 50, calculate delta G. By the way, there's a quick remark. There's pretty much always a unit inconsistency between delta H and delta S. Delta H is usually given in kilojoules, and delta S is usually given in joules per Kelvin. So make sure you convert the kilojoules and joules and make them the same. Okay. All right, so let's go ahead and plug all of this information in the equation up there. Delta G reaction at standard conditions is delta H reaction at standard conditions minus T times delta S reaction at standard conditions. All right, Jonathan. Uh-oh, Jonathan might be asleep and having a dream just like I did. All right, Christopher.
Sorry, what are you asking to do?
I've set it up. Just give me all the values. And there's one non-trivial value here.
I didn't even see those. Sorry. So it'd be negative 100.
Yeah.
Minus 298 Kelvin.
No.
No.
Yeah. What's the standard temperature in Celsius in this chapter?
25.
Nope, 0.
Oh. Oh, wow. It's right there.
25 in the next one. 25 in the next chapter. Yeah, that's what you're going to use in this chapter. 273.15. Okay. Times delta S, 50.
50. Yeah.
Yep, that's it. All right, can someone actually calculate this value for me? Actually, don't do that. Just tell me if the answer is going to be positive or negative. And yes, Jonathan, I see your message. That's okay. Okay, there you go. Thank you for your contribution. Jonathan has preemptively answered that for anybody else as a negative answer. So, is the reaction spontaneous? Yes, right? Delta G negative means the reaction is spontaneous. Yep. Cool. All right. Now the last part of the chapter is going to be a very, very, very simple one, but very interesting. This equation tells you that delta G depends on delta H and delta S and temperature, obviously, right? So if you know what the temperature is, if you know what the enthalpy is and what the entropy is, you can calculate delta G, no questions asked. You have all the information you need. But suppose we don't know what the exact values are. All we know are the signs on delta H and delta S. How much information can we derive in that case? Specifically, relating to the spontaneity of the reaction. If we know the signs of delta H and delta S, can we figure out the sign on delta G? And that would be our question. So this is just going to be sign of delta G, and hence spontaneity of the reaction based on signs of delta H and delta S. So here's where your arithmetic is going to come into play. You'll have to remember things like a negative times a negative is a positive. If you have a negative number and you subtract another number from that, that's going to be a negative. Stuff like that. All right, so let's come up with all possibilities. You have delta H, you have delta S, and we want to calculate what the sign on delta G is. It's pretty simple. What are all my possibilities? I can either have this as positive, this is negative. I can have this as negative, this is positive. Am I done? Good. Yep.
No.
What are the other ones?
Both positive and both negative.
Exactly. Both positive and both negative. All right, so that's the idea. So these are all the possible sign combinations delta H and delta S can have. And let's try and figure out what the sign on delta G should be. Just by plugging in the signs as opposed to numbers. Remember that this is delta H minus T delta S. Okay, so delta G is a positive value, and then minus, what is Kelvin temperature? Positive or negative? A better question is, can Kelvin temperature be negative? Does anyone remember that? think maybe we have an answer in the chat. Yes, very good. Kelvin temperature is always positive. So our T in the equation will always be a positive number, which is good. So we only have to worry about the signs of delta H and delta S now. Okay, so delta H is positive, minus temperature, which we know now is always positive, and delta S in this case we've taken to be negative. Cool. Let's do some mental math. We should do the multiplication first. What's a positive times a negative? Negative, okay. So let me just put this in parentheses. So it becomes a positive number minus a negative number. What about this part? What's the negative of a negative number? It's a positive. And so it's a positive plus another positive number, which we always know is positive. Aha. So this case has been, to quote Ben Shapiro, has been destroyed with facts and logic. So that's all there is, right? It's a simple sign logic, and you can figure out what happens in this case. Okay. So what can we say about the spontaneity? Not spontaneous. Okay, cool. Let's do this. Let's play the same game in the next one. Delta G, delta H is we've taken to be negative, minus T is always positive, delta S we've taken to be positive, and let's see what happens. So you have a negative number minus positive times a positive is another positive. What does this look like? A negative number minus a positive number. This looks like something like that. Negative 17, negative 3. Positive or negative? Or conditional? Does it depend on... Does it depend? Oh, come on, you know arithmetic. You know how to do this. Let's see. Depends on how negative delta H is. That's a thought. Okay, so let's test that real quick. You're saying that it depends on the relative magnitude of the two numbers. So why don't we check both cases? Let's do negative 17 minus 3, and let's do negative 3 minus 17. Those are the only two possible cases, right? One bigger than the other, and the other bigger than the first one. Okay. This thing comes out to a negative number, so it is this. Seems like it doesn't matter. Always negative, exactly. A negative number minus a positive number always gives you a negative number. Irrespective of which number is bigger, like we've checked. Okay, so this is always spontaneous. Okay. I have conveniently partitioned the sign combinations so that the first two are unconditionally spontaneous or not spontaneous, and the last two are conditional, which we'll see now. Okay, so delta G, all right, positive minus positive times positive. I'm just gonna go ahead and simplify the thing in the parentheses. It's a positive number minus another positive number. Now it depends. Here's an example, 3 minus 17 versus 17 minus 3. It's a positive minus positive in both cases. This gives you a negative, this gives you a positive. Depends. But suppose we still want spontaneity. Suppose we still want to make the whole thing end up negative. So which of these two terms are you trying to make large if you want the whole thing to be negative?
Entropy.
The second term, right? Yeah, no, not entropy. It's just the second term. Entropy is a part of the second term, but we can't change entropy for a reaction. Yeah. It's the second term that you're trying to dominate. And like I just said, you can't mess with the values of delta H and delta S. They're set in stone. A free variable is temperature. Temperature can be dialed. You can change that. That's okay. So if you want to make the second term, which is here, dominant, what would you do to the temperature? Yep, that's fine. I was replying to Jonathan. All right, so if you want to make the second term as large as possible, big, what would you do to the temperature? Make it high or low? Here's your second term. You want to make that blue box as big as possible. What should you do to the temperature? Make temperature a big number or a small number? Alexandra?
A big number.
Exactly. If you want the term to be big, well, make t a bigger number. Exactly. So the spontaneity happens, so spontaneous, if you crank up the temperature sufficiently. So spontaneous at high temperatures. We're not saying what temperature, but just qualitative description, high temperatures. Nice. All right, let's play the same game with the last one, and then we're done with this chapter. Negative minus, temperature is always positive. Delta S we've taken to be negative. So it's a negative minus a negative, which is like saying negative minus of negative is a positive. So this case boils down to a negative term fighting with a positive term. Which term would we like to see win? First term or the second one? For spontaneity. The first one, because we want the negative to win, which means in this case, you're trying to make the second term as small as possible. Aha. So what do you do to the temperature? Make it low, exactly. So spontaneous at low temperature. There. So much information extracted just by looking at signs. So you can have a question that goes, a certain reaction has solid and liquid, reactants solid and liquid reactants and gaseous products if delta H of the reaction, if the reaction is endothermic, I don't know what the problem is. What can you say about the spontaneity of the reaction? So you're trying to extract the signs on delta H and delta S from the wording of this question. Whose sign is obvious in the question?
Delta H.
Delta H, and what is it?
Negative. Oh no, positive.
Because?
It's endothermic.
Endothermic. So endothermic means delta H is positive. Great. Delta S, a little more tricky. Is the enthalpy going up or going down here? Grace, what do you think?
Oh, sorry, you can't hear me. Do you mean what charge is it?
No. Is the entropy going up or down? If the reactants are solid and liquid, and the products are all gas.
Is it going down?
Is it going down? Let's see. If we go back to where the criteria for entropy was, right here.
Okay, so it's going up.
Going up, yep. Solid gets converted to gas, liquid gets converted to gas, yep. Increases in both cases. Exactly. So it is positive. And then we just go back to the table and see what happens in that case. Or we fall in this case, positive, positive. Whoop, right here. So it's spontaneous at high temperatures. So that's the idea. One last question and we'll end it there. If an exothermic reaction needs to be spontaneous at all temperatures, oh, by the way, the first two lines I should add, not spontaneous and spontaneous at all temperatures. There was no temperature dependency in the first two cases. So add that. Needs to be spontaneous at all temperatures. What should the sign on delta S be?
Positive.
Positive. Let's see. Delta H is exo, so we are either in this case or this case. But we want the reaction to always be spontaneous, so we're in this case. Yep, and that matches with delta S being positive. So just different wording that you can expect to encounter. And that is it. That is this chapter. Pretty simple. All right, cool. Well, get some rest you've had a, a heavy week with all the exams and everything. And I'll see you guys next week.
Thank you.
Bye.
Bye bye.